Hello, I'm Andrew, and this is my fourth lab report. So the main purpose of this lab was to predict the behavior of circuits with parallel and series resistors and compare it to measured values found using multimeters and learning about the properties of resistors and capacitors. The main models and physical principles used are the loop rule, which is that the overall voltage drop of a loop is zero. Ohm's law, which relates voltage to the current and resistance. Conservation of energy and charge, and linearization of change in voltage compared to its original voltage, and also how resistors in series we can sum up the resistances to find the total resistance. So the preview of results, the first part, I calculated expected voltage calculations for a circuit, and I also measured it out and found the results were pretty similar. And for part two, using RC circuits, this is a graph of the linearization of the voltage over time. And for the system, it was the circuit, and the surroundings is just everything else. The assumptions I made mainly were that the multimeter measurements are perfect and the batteries are also at their exact marked voltage. Additionally, I assumed that connections are good and I didn't account for internal battery resistance. For part one, I created a series circuit with two 1.5 volt batteries and two resistors. The expected current I calculated using Ohm's law. I found it was 0.02041 amps, and it should be the same at both I1 and I2 theoretically. I also measured that they were the same, and it was around 0.02 amps. And if you flip the ammeter, insert it backwards, then it becomes negative 0.02 amps. And for the expected voltage calculations, overall voltage should be 0, battery should be 3, wire should be 0. And for the resistors, I multiplied the negative of the resistance times the expected current to get the voltage drop, because I'm expecting a voltage drop from the resistors. And for the actual voltage measurements, these were what I got. It was very close. And overall, for both current and voltage, the results were very similar, but they had some differences due to internal battery resistance, wire resistance, and overall imprecision in true resistance values. And for this is how I'm displaying the voltage drop over time in the circuit, or not over time, throughout the circuit. Um, it notice how it drops steeper on the stronger resistor. And then also when attaching a voltmeter, the ammeter reading does not change because voltmeters have very high resistance, so it barely affects the current. For the part two of the experiment, it introduces a capacitor and then it uses a light bulb as a resistor. And so for the first part, for the 10 ohm bulb, it took around 15.4 seconds to charge the capacitor. And then the light bulb initially is bright, but it dims out. And then after removing the battery, it took about 14.9 seconds to discharge, with the light also dimming. And for the 20 ohm bulb, it took 26.2 seconds to charge, 25.5 seconds to discharge. And then for continuing on, this is the linearization equation shown earlier. And then we want to solve for RC, which is the time constant, which is the time when the voltage difference drops to 1 over E of its original value. I used a stopwatch and was able to find the voltage drop at different times until 20 seconds, and plotted it out, fitted the line to it, and I was able to solve for RC, which is 5.952 seconds approximately. Possible sources of error are human error, which is timing, circuit setup, etc., multimeter inaccuracy, and the battery not being at the exact voltage described. One discussion question is, what if I were doing this in real life? Okay, so I did this in real life, and what is the difference with the ammeters, and how it affected the circuits. So since I did it in real life, the wires don't have resistance, and also ammeters do not have resistance virtually, so in reality the current measured would be smaller due to the extra resistance. And for the second what if question, what if I were doing it in real life and used a real battery, um, how would our ideal model predict the capacitor to reach full charge? Would it happen in real life? So in real life, the capacitor would almost immediately get charged up due to the lack of a resistor. However, this would not be immediate in real life, possibly due to a wire or battery resistance. Thank you.